Okay, this chapter 6 is oscillations. 6.1, describing oscillations. So first you have displacement, x, instantaneous distance of the moving object from its mean motions. Okay, so I give one example. Let's say if your oscillation happen in this way, follow the sine graph. So the vertical axis itself is called displacement. The horizontal axis is called t. So according to the definition here, the displacement is instantaneous distance. What is instantaneous distance? It's like the distance at any particular time from its mean position. Mean position is where? Is in the middle. This is the mean position. Okay, so when the let's say when the time is here, and then the displacement you have to go up to find out. So that is the displacement. Okay, so if the time is here, and then you can get this displacement. This is maximum displacement. Maximum displacement. So you can get displacement from the graph over here. Okay, so which is the vertical distance. Okay, vertical distance from the graph, that is the displacement x. Okay, next one, amplitude. Maximum displacement from the mean position. So this one I can add into the graph. Yeah. This is amplitude. Maximum displacement. Okay. Next one. Period. Period t. Time taken for one complete oscillation. So one complete oscillation is here until here. This is period. Okay. Frequency. Frequency is number of oscillation per unit time. So frequency is 1 over period. So frequency 1 over period. Okay, next one. Angular frequency. Rate of change of angular displacement. Rate of change of angular displacement. Omega. Okay, maybe you feel like, oh, omega, I learned before. In chapter 1 of our physics lessons, omega is angular velocity. Angular velocity. So that is more suitable to be used in circular motions. Okay, circular motion. We use angular velocity. The unit is radian per second. Radian per second. So over here, this is oscillation using angular frequency to represent angular velocity. It is the same thing, It is how much radian in 1 second. How much radian? How much angle in radians that has been done in 1 second. Okay, so that time when we learn omega, right? We use angular displacement over time. Then I also said that time there is a shortcut. We can set our theta as 2 pi. Then the time will automatically become period. And then 1 over period is frequency. So it becomes 2 pi frequency. So that's why this same thing come out again. Omega equal to 2 pi f. Okay. So next one, phase difference. Phi. Measure of how much one wave is out of step with another wave. Phase difference. That means difference in angle. Okay, different in angle. Okay, so for example, a phase difference of 90 degrees. Okay, let's see. I put a wave here. So this is the common one, sine graph. So if let's say I have another phase which has the sine graph earlier. Okay, to find the phase difference between these two waves, the blue color and the red color, to find the phase difference. So it's good to know the two same points. Okay, it's good to decide two same points. So for example, let's say I choose the maximum point, and we find the difference in angle in terms of radian. Okay, so let's say, for example, when I make one round, it is here. This is one round. This value, let's say it is 2 pi. One round is 2 pi. Here is 0. Okay, then half of it will be pi. This is pi. Okay. And this one will be pi over 2. So the phase difference is minus. We minus pi with pi over 2. And then you get pi over 2 as the phase difference in angle. Okay, phase difference. This is phase difference in angle. But you have to remember one thing. You have to remember one thing in this way. They give 2 pi, pi, and pi over 2 if there are radian over here. Okay? But if it is time, then let's see whether I can get any example or not. If I have any example, then I can show you how this formula works. Okay, so let me check the past paper first. And just find out a suitable example to go through with you. Okay, so let's say, for example, another example. Okay, so this one I change to theta first. Theta. So for this case, it's theta, the angular displacement. Okay, so I can get phase difference directly. But if let's say they give you time, and here is displacement. Okay, so let's say I have value like this. Same graph. So let's say I have 0. 2, 4, 6, 8, 10, 12, 14, 16. Okay, now I have another graph. Same graph. You know the phase difference is pi over 2. Okay, so now how are we going to deal with it? So again, if we drag it down, like what I said, to find the phase difference, you have to choose two same points. And now we have a formula like this. Okay, so let's see how we use it. Okay, so based on the formula, we have to use that. Okay, so we just use it. The time span here is 2 seconds. The period, 1 round. Period is here to here, 8 seconds. 8 seconds. So let's say this is time in 8 seconds. The 2 point that we choose is 2 seconds. Okay, so then phi, the phase difference is 2 pi times 2 over 8. So which is 1 over 4 times 2 pi over 2. So this is how we use the formula. Okay, so we just use it in that way. Actually, that formula, right? I mean this formula. This formula is actually ratio. It's actually ratio. Okay, so what kind of ratio are we talking about? Imagine that if I rearrange phi over 2 pi t over t, it's actually ratio. Imagine that phi is the smaller angle that you're supposed to find. So you have to use the smaller time to help. 2 pi is the angle of one complete oscillation. Then you have to use the time for one complete oscillation, that is period. So they are in proportions. So they are ratio method actually. Okay, so we use the formula in that way. If they give time, so if they give time, use this formula. If they give theta, angular displacement, straight away minus the angle. Straight away minus the angle. That angle is angular displacement. This answer is straight away the phase difference. Okay. So where t, let's see. Where t is the time period and small t is time lag between wave. Time lag means the difference in time. You choose two corresponding time and minus, then you can get the time lag. Okay, so now let's see 6.2, simple harmonic motion. Okay, so what is simple harmonic motion? So the definition is here. The first point, simple harmonic motion, acceleration proportional to displacement and directed towards a fixed point. Okay, so to understand this simple harmonic motion, so let's see one example. So I put an example at the side here. Okay, so let's say you have the ceiling is like this, and then you hang a pendulum with a bob like this, and then you make it swing. Okay, so it will swing in that way until it reaches here, then it will swing backwards. Okay, so this is a simple harmonic motion. Okay, so let's understand it through a few parts over here. So I take the middle point here as the fixed point. Fixed point, yeah? Or you can also call it mean point. Okay, so the simple harmonic motion, the definition here, they talk about two things or two quantities. The first quantity is the acceleration, and they say the acceleration is directed towards a fixed point. So this is the fixed point. So the acceleration is always directed towards the fixed point. Okay, that's the acceleration. Okay, so here as well, directed towards the fixed point. And the displacement is from the fixed point. Okay, displacement is this way, x and x. Okay, so that's the thing. At the meantime, you can see something. First of all, you can see the acceleration is proportional to displacement. That's the first thing. Okay, acceleration is proportional to displacement. That means the higher the displacement, then the greater the acceleration. Okay, so that is one thing. The second thing is they are in opposite directions. Okay, as you can see clearly from here, the direction, displacement is going out, then acceleration is going in. So they are in opposite direction. So acceleration and displacement are in opposite directions. Oops. Opposite direction. Okay, so these are the two important points. Okay, now let's see more information. Requirements for simple harmonic motion. So the first thing is it must be the mass that oscillates. The mass that oscillates. Okay, so for example, this bob is oscillate. It is having a mass here, so the mass that oscillates. So example for the mass, for a situation where mass, it is not mass that oscillate, is this one. So I give example 2. This is example 1. So example 2. So example 1 is where mass oscillates. The bob is oscillate due to its mass. Okay. The second thing is I give an opposite example. So if let's say I have a conducting sphere, oscillate between two charged conducting plates. So this is not simple harmonic motion. Okay, so imagine you have a positive plate, negative plate. So let's say this is positive, and let's say this is negative. Okay, then this is the ceiling, and then this conducting sphere is oscillating here and here. And this is not a simple harmonic motion because the oscillation is not due to the mass, it's due to the charge over here and there. Okay, so we have the charge on the conducting plate. Okay, it oscillates because of the charge that attract or repel. It's not because of the mass. Okay, it's not because of the mass. So next point, positions where mass in equilibrium. Okay, so there must be a positions where mass in equilibrium. So what position is that? It is the fixed point or the mean point. It is this point. Okay, and the third properties, restoring force that acts to return mass to equilibrium. Okay, so there is a force that is proportional to negative x. Okay, so what kind of force is that? So I can put it here. You know, F equal to ma, Newton's second law. If the acceleration is pointing back to the fixed point, so we should expect the force also point back to the fixed point. So the force is in this way. Okay, so the force is in this way. So from here, you will understand something. The force and the displacement are having opposite sign. Okay, opposite sign. So now because of this, we have the equations. So you see the next point, defining equation of SHM. So this is the formula, A equal to minus omega square x. Okay, minus omega square x. Okay, so this is the formula for simple harmonic motions. Okay, and then of course the omega here is uh, the velocity, the angular velocity. Okay, so you have to know that. And then let's see the graph here. Or at the same time, you can see something also like A equal to minus omega square x, right? So you can also see, because omega square is a fixed value, so we can also see A is proportional to negative x. So the acceleration and the displacement have opposite direction and their value are proportional. Okay, proportional. So now let's see the graph. The y-axis of the graph is A, acceleration, and then the x-axis is x, the displacement, and then this point, this point is where you have actually x equal to, okay, so I explain a bit. What happened at this point is where the displacement is equal to the amplitude. Displacement equal to the amplitude, and then you substitute x equal to a into a equal to minus omega square x to get a equal to minus omega square a. So to get minus omega square a. Okay, so the value shouldn't be here. The value should be here. Should be here. Minus omega square a. Should be there. It is acceleration, right? So acceleration is the y, so that's why it should be there. So this is an error. So this x-axis should be a then. Should be a, yeah. The point, the value on the x coordinate should be a. So likewise, this one is an error again. So this value should be minus a. Should be minus a, yeah. Then you substitute minus a. Imagine that you substitute minus a into the x, and then you get negative and negative that cancel off. Then you get positive omega square a. So let me write down the working here. X equal to negative a, so a equal to minus omega square minus a. Negative cancel off, omega square a is the final value. So that's why this value, which is a positive value, it should be positive omega square a. Should be this value. Okay, so that is how we understand the graph. And okay, so from here, what we can see is when the displacement is maximum, okay, as you can see here, when the displacement is maximum, then the acceleration is maximum also, but opposite direction. Opposite direction, okay, opposite direction. So which means when the pendulum bob reach here, the acceleration is maximum but opposite direction, meaning that the force to pull it back is the greatest. And because of that, it stops here and then it will turn back afterwards. So remember that, when the displacement is maximum, the acceleration is maximum but negative, but opposite direction, meaning that the force is maximum but act in opposite direction, making the bob stop from going anymore to a greater displacement. It stopped from going anymore, so it turned backwards. Okay. Likewise, when it is going to this side, let's say this is negative displacement. So when they reach the maximum of negative A, so when the x is negative A, okay, negative A, maximum displacement already. So at that time, it will have maximum acceleration also. So this maximum acceleration, as you can see here, the highest point, so making the force to be maximum as well. So as you know, the force is acting this way, so the bob will not go any further. Yeah, will not go any further. It will just stop here because the force is the maximum here to pull it back to the fixed point. So basically, it is like that. And now let's move on. Okay, this side. The negative sign in the equation represent that acceleration and x are in opposite directions. Acceleration is always directed towards the mean point. Okay, so this one I explained already. Now let's move on to 6.3, equations of simple harmonic motion. Okay, so we start from displacement. X equal to x naught sine omega t. Okay, so when you look at this equation, you will feel like, oh, this one is the same with the one that we learned before, right? So which is the sine graph. The sine graph, this graph. Okay, this graph, the sine graph. Okay, they follow the sine graph. So this is displacement versus t. So same with this one, displacement versus t, and it's a sine graph. Okay, so of course it is, okay, I draw the small one here for comparison. So if this is the equation, the graph is sine graph. Sine graph. So this is t, this is x. So if it is sine graph, that means the initial condition is they start from the origin. As you can see from the graph, they start from origin. So meaning that if I use the pendulum bob to be my example, so that means if our graph is sine graph, right, that means the oscillation start from the fixed point or the mean point. Then you push it here, then it will start oscillate. Okay, that start from the fixed point. But the thing is, we no need to start from the fixed point all the time, so we can start from, let's say we can start from the maximum displacement here. Yeah, we can start from here also, we can start from here. So if you start from here, right, you start from a maximum displacement, right, so we don't use sine graph anymore. So that's why there is a second option here. So the second option here is where you can see this equation, x equal to x naught cos omega t. So meaning that it doesn't start from the mean point, it starts from maximum displacement. The x naught, okay, x naught that I mean is this one, the x0 here. This is called x naught. So it starts from maximum displacement. Of course, you can call it amplitude also. So that's why it follows the cos graph and it looks like that. So x versus t. So it starts from x naught. Now we have these two equations now. Okay, so now let's see the next point, velocity. So velocity, we learned from mathematics. We know that to get velocity from displacement, we need to do differentiation. Okay, we need to do differentiation. Huh? So imagine that if I differentiate my displacement, okay, if I differentiate, so right here, I differentiate, so I will get x, no, I will get dx dt equal to, okay, so to differentiate this with respect to t, right? So we differentiate the angle first. We differentiate omega t, yeah. So differentiate omega t, we get omega. Okay, we get omega. So when you get omega, then we write it as x naught omega. Okay, so x naught omega. Then differentiation of sign is cos. Then omega t we write back. Okay, so after differentiation, it becomes x naught omega cos omega t. Okay, so after that, this x naught omega, right, is actually the maximum velocity. X naught omega is the maximum velocity. Then the cos omega t remain. So that's why you can see the next formula written here. V equal to V naught. V naught is the maximum velocity. So cos omega t. Cos omega t. Okay, so that's the formula after we differentiate. And then after that, for this side also, if your displacement equations follow this formula, then again we differentiate it. Okay, so we differentiate. So you will get dx dt equal to x naught omega. Differentiation of course is negative sign, omega t. Then simplify it and you will get that, where again we change x naught omega to v naught. Okay, so that's why we have this v naught here, because x naught omega. So x naught omega is v naught. It's x naught omega, we change to v naught. Okay. Now, once you get these two formula, right, then you may wondering, how about the formula in the middle? How we get this, or what kind of formula is this? Okay, so what you do here is you have cos omega t, yeah. So you have to make use of the power 2, the power 2. So you have to make use of cos square theta equal to 1 minus sine square theta. So this is the mathematics formula, the trigonometric identity basically. So you have to make use of this, and then you will get that formula. Okay, you will get that formula by using this trigonometric identity. Cos square theta equal to 1 minus sine square theta. And then you will get this. Okay, so let's say I do it at the side here. Okay, so here I have V equal to V naught cos omega t. You know, cos omega t is equal to cos square omega t square root. So I square and square root purposely so that I can use the formula. Okay, I can use the formula where V naught, the trigonometric identity, 1 minus sine square omega t. Okay, so 1 minus sine square omega t, and then after that, okay, this omega, this is V naught. Okay, V naught. Okay, so if like that, I change the V naught back to x naught omega. X naught omega. You know V naught is x naught omega. So from this part we know that x naught omega is V naught. So I put it back here. Okay, then square root 1 minus sine square omega t. Okay, now what happened is the omega I leave it outside, but the x naught, right, I change it to x naught square and square root. The reason that I do so is so that I can bring it into the square root there. Okay, so now we get omega x naught omega square minus x naught square sine square omega t. And then after that, omega. Okay, so as you can see here, x naught sine omega t is equal to x. Huh? So that change x naught square sine square omega t into x square. As you can see here, x square. Huh? Okay, so after that, you will get x naught square minus x square. So that is v. Okay, so we get this equation. Okay, now you already know how to get that. And then, how about the other form? Okay, maybe you are wondering the other form. Okay, so we have another form here. So v equal to minus v naught sine omega t. So actually it works in a similar way. So let's take a quick look. I'll do it at the side here. V equal to minus v naught sine omega t. Okay, so I do the similar thing. I purposely change it to sine square and square root it again so that I can use identity. The identity is 1 minus cos square omega t. Okay, then the v naught is actually x naught omega 1 minus cos square omega t. Then I purposely change the x naught to x naught power 2 and square root. I create the square root so that I can combine with the square root at the back there. Okay, now both have square root, so I can put it inside. So it become, I can multiply x naught square with both terms at the back. And then after that, imagine that based on the equation here, x equal to x naught cos omega t. I substitute it at the back here, so it becomes x. So because of that, I get minus omega x naught square minus x square. Okay, just for remark, this one, let's say I call it equation A. This one I call it equation B. So this is where I substitute A. This is where I substitute B. So V equal to omega square root this, or V equal to negative omega square root that. Okay, so that's why you have this formula in the middle here. So it is the differentiation and simplified it. Okay, so let's see more information. This point, what they say is maximum velocity at equilibrium positions and minimum at extremes. Okay, so to understand this is not too hard. Let's see the example of our pendulum bob. So they say maximum velocity at equilibrium, so which means this point. Okay, so imagine when the pendulum bob swing around, so it is the fastest at this point, and then 0 at this point, 0 at this point. So here is the maximum velocity. Maximum velocity means dv dt equal to 0. That means acceleration equal to 0, which is true also, you know. You see the graph, acceleration equal to 0 here. When the displacement is 0, acceleration is 0. So meaning that this point is maximum velocity. Okay. So when they reach here, this is called the extremes. Okay. When they reach extremes, maximum displacement, then the velocity here is 0. Velocity is 0. Okay. So it's here or here. The velocity is 0. Yeah. So of course, acceleration is maximum. Yeah. So you can see something like that. Now let's move on. Even this equation can explain the same thing. So imagine that when the pendulum bob reach equilibrium, that means reach the mean position. So the x you replace with 0. The x you replace with 0. When you replace with 0, then you will get plus minus omega x naught. Imagine the x naught you have square and then you square root, it becomes x naught. So omega x naught is maximum velocity. Okay, at mean point, at mean point when this is 0, you will get plus minus omega x naught. That is maximum velocity. This one also, minus is also maximum velocity. But when the pendulum bob stay at extremes, so your x is x naught now. If your x is x naught, so x naught square minus x naught square will end up with 0. Then velocity becomes 0. So even this equation can explain this statement. Okay, now we move on. Acceleration. The acceleration. First, let's see how we get this formula. So we have to differentiate one more time. So let me show the differentiation here. Okay, so okay, let's say yeah, differentiate. Then we get dv dt equal to, okay, now let's say I don't want to use v naught. I use x naught omega as my constant in front. So the x naught omega will remain, and then differentiate cos omega t. I have to differentiate omega first. So differentiate omega t. Differentiate omega t first. Differentiate omega t. Differentiate the angle. You will get omega. You get omega. Differentiate the angle. You get omega. So x naught omega multiplied with omega, you get x naught omega square. So that is what happened to the front part. X naught omega square. And then differentiate cos. Differentiate cos, you get negative sign. Okay, so that's why here negative sine omega t. And we have to know that the front part, which is all this, is the maximum accelerations, which is a naught, Okay, they don't do anything. They just leave it like this. Okay, they leave it like this. But you have to know that because simple harmonic motion, the formula is this one. So if you put x naught inside, then you get maximum. So this is the maximum acceleration. Okay. Now how about this part? This part, it works in the similar way. You just need to differentiate it. Okay. You have to differentiate. Let's say I differentiate this one. Okay. Differentiate. So differentiate v become dv dt. And again, I don't want to use v naught as my discussion. I use x naught omega as my constant that stay in front. So to differentiate sine omega t, we differentiate the angle. We differentiate omega t first. Differentiate omega t, we get omega. And omega multiplied with x naught omega, we get x naught omega square. So together with the minus in front, we get minus x naught omega square. And differentiation of sine become cos omega t. And because of that, you get this formula. By factorizing the omega square, you get the formula. Okay, so after that, you will realize for accelerations, you will see this part as the maximum acceleration, which is negative omega square x naught. Okay, so again, this part is maximum acceleration. This is maximum acceleration. But of course, if you replace equation A, if you replace equation A into this bracket, so what we get is, as you can see, x naught sine omega t, here x naught sine omega t is x, so if you replace it here, then this part becomes x, and you will get this equation, minus omega square x. Likewise, for this equation, if you replace the thing in the bracket here with equation B, then what happens is the bracket become x. It become x. So it becomes minus omega square x, which is this formula then. Okay, this formula. So at the end, we have to say that we get this formula, the simple harmonic motions. Okay, so we will get that formula at the end. So